Okay, so we are already done with the bracketing method, or both the bisection and the false position method. Other method to solve the root of nonlinear equation is we call those the open methods. So in the bracketing methods, if you remember, no, we have an interval, no, we bracket, we contain, and then we ensure that between the interval there is a solution, no, there is a root of equation. In the open methods, no, we do not bracket, no, we do not contain the root of the equation. So in the open methods, we have two methods. We have the Newton-Raphson and the second method. Actually, the second method, this is similar with the false position method, but not entirely, because the false position method is a bracketing method. The Newton-Raphson method, no, in the second method we apply the second line. In the Newton-Raphson, here we apply the tangent line. So again, the roots of the equation, or we call this the zeros of equation, these are the values or the set of values of x where the function of x is equal to 0. So let's proceed with the open method. So in the open method, only initial guesses is assumed, and then we have a trial and error, no, without the use of brackets. So dili na ta mag-check if there's a change of sign between the functions of the lower and the upper guess, or the initial guesses. So in the open method, no, this is at times more efficient, but uh, does not always yield the solution. So mo ni siya in the open method, dili siya always converging, mas dali siya, but at times it's not always applicable, because the open method, no, when we use the open method, the solution or the calculations might diverge. So the first open method, we have the Newton-Raphson, so, or also called the Newton's method. When the function of x is 0, where f of x is continuous and differentiable with no solution near a given point, usually converges fast and will not converge if the x1 is not close enough, or when f of f prime x1 is close to 0. So methods such as the bisection and false position method of finding roots of nonlinear equation require bracketing. So both of those requires the bracketing method, the bracketing of the root. So, but this one in the Newton-Raphson, we do not contain the values. The root is not bracketed. That's why we call this the open method. And then we only require one initial guess to start the iterative process. So convergence in the open methods is not guaranteed, but if the method does converge, it does so much faster than the bracketing method. So mo pa yung nakapabor with the Newton-Raphson. Newton-Raphson mas dali siya mo converge than the Newton-Raphson or the open methods mas dali mo converge with the bracketing than the bracketing methods, if there is a convergence. So diri mo na siya ang derivation with the Newton-Raphson method. So again, no, in the Newton-Raphson method, no, we made the use of the tangent line. So okay, so let's say we have a curve. So the curve, this is the function of x. Now karon, if we get a certain point and we put a tangent line there, again the tangent line only intersects at a single point in a curve. Now that point, that tangent line is the slope of the curve, and we know that the slope of the curve is the first derivative of the curve, diba? So let's say we have xi will be our x sub I will be our initial guess. So the value of y there of of the x sub I, that we call that the f of x sub I, or the function of x sub I. And then the first derivative of that point that forms the tangent line, that is the slope of the that function. Again, so the slope of the function, but that is the first derivative, and then that is the rise over the run. So the rise is this one. This is the f of x sub I minus 0 all over x sub I minus x sub I plus 1. So again, no, if there's a tangent line, and then if we extend that, no, it will intersect at the point along the x-axis. Kani siya nga point 3, no, that is when y is equal to 0 at this point. So So this part here, this point where the tangent line is intersecting the x-axis, we call that the x plus 1. So that's why we have here the xi minus x sub I plus 1. Now this is the difference between these 2 points, the rise over the run. Now we are going to get the new point, since this is the new point, until makaduol siya sa kuan, sa correct answer. So our approximated root, no, instead of using xr, for this one we are using x sub I plus 1. Which is equal to x sub I minus the function of x sub I all over the first derivative of that function. More ni siya. You have the initial assumption, and then to get the approximated root, which is this is we have here the old value, and then minus uh, the function of that x, of that first value, or the first approximated or initial guess, divided by the first derivative of the function of the f of or the first derivative of the assume or the initial guess. So mo na siya yung algorithm, no? You have the initial guess, and then compute for the function and the first derivative using your initial guess, and then you're able to calculate the second point, the third point, until you arrive at the specified criteria kung kano sa kamuhunong. So we have here, no, this is a more detailed curve. We have a curve, and then we have our first assumption, and we have the slope and the tangent line. So this is the second guess, this is the initial guess, and then this is the second point calculated using this formula. And then kuhaan po mo na siya tangent line there, we just apply there until magkaduol ta sa correct solution. Now these are the drawbacks, no, disadvantages of Newton-Raphson divergence at inflection point. So when we see an inflection point, no, these are the points where the concavity changes from up to down or down to up. So for example, no, we have a curve. So yung ka-inflection point mo na siyang point along the curve where instead of let's say paano mo na siya, there's already the change of direction, no? Instead of from up to down, it changed from down to up. So mo na siyang ga-divide sa curve. So at that point, no, if the selection of the initial guess or iterated value of the root turns out to be close to the inflection point of the function in the equation, Newton-Raphson method may start diverging away from the root. So, di ba, we have a tangent. Buta na to diya siya. Gagamit mo tag tangent. So, pag maanam na siya kaduol diha, maanam na sa layo sa root. Kaya mo change man siya yung slope. And then division by 0. So, sabo na siya, no? Let's say the first derivative is nadiri ang tangent line, this is the slope, no? So the first derivative is 0. So usab ni sa problem with the Newton-Raphson, if we arrive at this point, no, and then oscillations near local maximum and minimum, results obtained from the Newton-Raphson may oscillate about the local maximum or minimum without converging on a root, but converging on the local maximum or minimum. Eventually, it may lead to division by number close to 0 and may diverge. So, manino, let's say we have a curve, and then natin mga initial guesses, and then maabot din manam siya kalayo. Tapos root jumping, we have this root jumping. So in cases of ingan, dagan siya roots, pwede nga initial guess nimo, let's say initial guess is diri, and then i-atras din ta dito, diba, for the Newton-Raphson. Tapos from there lahi na sad nga value, so on and so forth. Nasi nga nga problem. So let's say initial guess diri, and then from there ana na sad anong kakalayo, no, sa imong roots. So instead of katong pinakadulong ta nga root imong makuha, nag-ambak siya sa pikas. This is true for there are many oscillations, no, there are many waves. So that is the problem with the Newton-Raphson.